Does anyone have any questions before we get started with the regular material? I sent out an email last night saying that the reader's ready, and you can pick it up at the Copy Central that's on Northside. This is what it looks like. Northside is if you want to exit after class, rather than going down the stairs or down the elevator, you can exit out to the street and simply walk down Hearst until you get to Euclid, and it's 2 storefronts past there. So this is the reader, and it's available, and you'll want to read it for your first homework assignment. I posted the first reading, which is about 15 or 20 pages in the reader. Also, yesterday, Wayne posted some very detailed notes about using R, which will be really helpful for you in doing your first homework assignment. And we'll be doing a little bit of, we'll be using R a little bit in class if we have time at the end of lecture today. So what I thought we would start today with is going back to looking at the distributions of qualitative variables again. And this time go a little deeper into what this density or what it means and how we can use it to understand the distribution of our quantitative variables. And at the very end, we'll get into a little bit of what to do with qualitative variables. So birth weight is the variable that was measured on our infants that were born in Oakland Kaiser Hospital in the 1960s. And remember, these are all male births. And we started looking at the distribution of the birth weights. And essentially what a distribution is it's sort of saying what are all the different possible values that we've seen in our data and how many different occurrences of each of these values are there. So in particular, for 121 ounces, there are 24 babies in our Kaiser study that were born weighing 121 ounces. A distribution table tries to take all of that information and collapse it into intervals or bins to make it a little bit easier to comprehend. And your choice of bins can help uncover the shape, the underlying shape of the distribution. Your bins do not have to be equal in size, and in fact, oftentimes it's better not to have them equal in size in order to get a sense of the shape of the distribution. Where there's a highly dense region, you sometimes want to have really small bins, and out in the tails, where there aren't very many observations, you often want to have larger bins or intervals. So as an example, if we look from 90 to 99 ounces inclusive, that means including 90 and including 99, there are only 5 babies in that category. So a baby that weighs 5 pounds at birth would be 16 ounces to the pound would be 80 ounces. And so 90 to 99 is a somewhat small baby. Then a density plot, which is what we're looking at, and in section yesterday you hopefully had a chance to start making these plots. A density tries to show the shape of the underlying distribution. So we looked at the density plot already for the male babies born in the Oakland Kaiser Hospital. And just as a reminder, this is what it looks like. We saw that it's got a main peak at about 120, and it's roughly symmetric with possibly looks like a slightly longer left tail. So what does that density mean on the y-axis? That sort of says if we look at a particular little interval, such as 100 to 105 or 120 to 125, the height of that bar tells us kind of like how many babies we've crammed into that little region. So the higher the density value says that there are more babies in that little interval. And so in this case, the 120 to 125, its value for its density is roughly 0.02, 4 or 3 or something like that. Whereas for 100 to 105, the height of that strip is roughly 0.012 or so. So we can use a density plot to figure out proportions within our observed data. And in particular, the area under a density curve equals either 100% or 1. 1 meaning the total, or 100% meaning the total. The way our density plots work in R is the area underneath it is 1. And so if we look at just some portion of that density plot, that gives us a rough estimate as to the proportion of individuals, babies in this case, that are within that little interval. So for example, the area under the curve between 120 and 131 is, in this case, I know the answer is 25%. So 25% of the babies are within between 120 and 130 ounces. Here's an example of how we actually do this calculation. So roughly, if we have a small enough bin, we can kind of cut it off at the top, flatten it out, and think of it as a bar. In fact, that's essentially what a histogram's doing, is it's making things a little easier by flattening out those intervals or bins. So from 100 to 105, the width is 5 ounces. The height is 0.013. And so to get the area of that strip, I just multiply the width times the height, and I get 0.065, which is 6.5%. So 6.5%, roughly 6.5% of the babies are in that interval. Why am I saying roughly? Not quite. It is true this is statistics, but that's not quite what's going on with, yes? Because it's not a perfect rectangle? That's true, it's not a perfect rectangle. I'm actually referring to a slightly different thing that's going on with this smooth curve. Yes? Yes? No? Changed your mind? Yes?
The height is approximate.
That's what I think you were saying, that the height is approximate. What's going on here is that they're actually, do you want to make a comment?
I was going to say that you smooth the curve out a little too.
That's the answer I was looking for, is that I've smoothed the curve out. Now, you are all correct. Those of you who said, well, the height's approximate, that's correct. I'm trying to turn this into a little bar to make it easy to calculate that area. But there's something else going on here, which is the actual individual observations. I'm taking them and I'm smoothing them out to get this curve. And I'm going to talk to you a little bit about how that smoothing happens so you have a better understanding of what a density plot looks like. So that's what this next plot is about. So what is this smoothed density that I'm talking about? I took just a really simple example with only 4 observations, and I made a rug with them. Remember, a rug just puts a little tick mark or string at each of the observations. I only have 4 observations. These are these 4 made a red rug. There's one at 3. There's another at 5, 5.2, and 8. I only have 4 observations. What's going on with a smooth is it takes what's called a kernel function, and they can be different shapes. This one looks very normal. And to come up with your estimate of your density at the point in particular, I'm trying to come up with my estimate of my density at 4.75. I put a little smooth kernel on top of 4.75. And what I do is I pull in the information from the other observations, the neighboring observations. The closer they are, the more I'm using them to come up with my estimate. So the observation that's way out here at 8 is really far from 4.75. And so I'm basically not using that to come up with my estimate at 4.75. So I'm essentially taking the height of the curve, the kernel, at each of these observations, and I'm stacking them on top of each other. So in other words, I'm smoothing things out to sort of say, you know, that baby that weighed 90 ounces might have weighed 90.3 ounces or 90.5. I, in fact, only measured the baby's weight to the nearest ounce. So, and that other babies that I didn't observe could easily have weighed 92 or 92 and a half. And I've got this set of data, but I'm trying to come up with a slightly more abstract version of what I think the distribution of birth weights are. And so what I'm going to do is take the birth weights that I've observed, and I'm going to create a smooth picture of what I think the real distribution is. And that's what we're doing here is for every point, I move, every place where I'm going to come up with a point on my curve, I move this little kernel along, and I see the height of that kernel, the value of the kernel at each of my observations. So when I'm really far away from where I'm doing my estimate, I don't contribute at all to the density. And when I'm nearby, I contribute a lot. And so I've color-coded this. Above 3, there's a purple bar. Above 5, there's a turquoise bar. Above 5.2, there's a blue bar. And above 8, there's a black bar. It's really tiny. You can barely see it. And I'm stacking all of these at 4.75. And I keep doing that as I move along. So that's what we're calling as smoothing. It's sort of like a weighted average. Yes?
How did you pick 4.75?
I just chose that. I'm going to estimate my, create a density plot that's smooth. I need a value at every single position. So I chose that as an example to show what would the density look like. How do I compute it at 4.75, or how does the software compute it? So I continue to move those kernels along, each time doing that exact same process, and this is the shape that I get in the end. So you can see how those, at 4.75, I've got my purple, stacked on top is my turquoise, stacked on top is my blue, and just stacked on top is a tiny smidgen of black. And that's my estimate for the density at 4.75. And to get all the others on my thick blue, solid blue density plot, I do the same thing. I keep moving this kernel along to sort of say, this is what I'm going to use to smooth things out. Okay? So my question to you is, what do you think happens if I change the kernel and I make it much skinnier? Yes, in the back? Values that are farther away have even a smaller contribution, which means the only thing that's going into the smoothing are really close observations. And so what might the final density look like when you have a smaller kernel? Opposite. It's going to bounce up and down when it hits a few observations. Flatter is the answer to the other question, is what if I make my kernel big and flat? That's going to pull in the information from a lot very far away. And so then whether I'm here or here or here, I'm roughly pulling in the same observations, and so it doesn't change as much. So here's some examples. So this is called picking the bandwidth, which is how wide or narrow is your kernel. And R does that for you automatically, but it also allows you to change the kernel's bandwidth if you like. So it's called the bandwidth, which is basically whether you have when it's small, you've got a very narrow peaked kernel, and when it's large, you have a very broad flat kernel. Here it is for a broad flat kernel. Same data, haven't changed it. My 4 little observations. But notice my kernel is it's flat. It's much flatter and more spread out. And so the contribution to creating the estimate for the density at 4.75 is nearly the same. My observation 3 and my observation 5 and 5.2 contribute nearly the same amount. So that's sort of saying, I've got a lot. I'm really not sure where the real data are. I'm going to really smooth things out a lot. That's what's going on here. And so you've got a much flatter density plot. On the other hand, when we have a really narrow one, as suggested by someone in the back, then when I move along, there will be times when there's no data, and so my density estimate's going to drop dramatically, and there will be times when I'm very close to data, and it'll really spike up. And so that's what's going on, is now at 4.75, the observation at 3 contributes next to nothing. The observation at 8 does contribute nothing, and it's only the 2 observations at 5 and 5.2 that make any contribution to the density plot, the density curve, at 4.75. And as soon as I get a little further away from 5.2, then I'm in sort of a place where there's a gap and no data, and the density plot drops off dramatically. So it's an art trying to pick the right kind of bandwidth so that you, ideally, what you want is you want to be able to see the shape of the distribution. You don't want to just have something that's absolutely flat and says, oh, my data's somewhere in here. And you don't want something that's super spiky, that's essentially not much different from a rug, which is sort of telling you where all the individual observations are. So that's a real sophisticated concept. Here's what happens when we apply it to the babies. So here's the band. When I set the bandwidth to 3, I get something that's really smooth and looks just about like a bell curve. When I make the bandwidth only 1, then I start seeing the little sort of concentrations of birth weights. They are still roughly the same shape. They're not all that different from each other, but the lots of squiggles up and down is showing you more of where the actual observations are. So remember that no matter what, whether I have a very squiggly density plot or a very smooth density plot, it's always the case that the area under the density plot equals the proportion of the observed values. And now you know when I say roughly why the other piece of roughly has to do with the smoothing. So when I look under this very squiggly one and say, what's the area here? Or I look under the very smooth one and say, okay, what's the area here? Because I'm smoothing my observations, I'm sort of spreading them out to contribute to the density at different places, I'll get slightly different answers. Questions about that? So you're going to be playing a lot with density plots for your first homework. In particular, you're going to look at the variable gestation, and you'll also be looking at birth weight as well. Now's a good time if you have a question. No? Okay. So I'm going to beat this to death. About what a density plot is. Many of you have worked with histograms since you were probably in 3rd grade. A histogram is like a density plot. It's sort of a special case of a density plot. It's where we take you can think of it as we're taking a density plot that's a smooth curve, and we're chunking it, looking at specific intervals, and we're sort of flattening out the curve. So essentially, the height of the bar times the width of the bar gives us the area, which is the proportion of the observations that are in that bar. So it's the same thing as with a density plot. That area is proportion. That's very different from a bar chart or a bar plot. They are two entirely different things, and people blur the distinction between them. With bar plots, the height is the proportion, and the width means nothing. You can have really big, wide bars or very skinny, narrow bars. Doesn't matter. It's just the height that you're looking at to get the proportion. With a histogram or a density plot, the height is the proportion per whatever the measurement is, such as ounces. So here's where units really help you. The height is density, which is proportion per ounce, and the width is ounces. When you multiply those together, the ounces cancel and you get proportion. Okay? So a density plot or a histogram, the y-axis should be proportion per whatever unit you're measuring on your x-axis. Is that clear? Okay. When you have a density plot or a histogram, the y-axis should be proportion or percent per whatever unit you're measuring on your x-axis. So whatever unit you've measured in your terms of your variable. If it's birth weight, it's ounces. If it's height, it could be centimeters or inches, etc. All right, so again, back to our really simple example with our only 4 observations. The rug is still there. Remember, there's a point at 3, 5, 5.2, and 8. If I make a histogram of this, my bars do not have to be the same width. So I chose 3 bars. The first one goes from 0 to 4. The next one goes from 4 to 6. And the last one goes from 6 to 12. So if I want to say, okay, what proportion of my observations are in the bin from 4 to 6, I take its width, which is 2. I look at its height, which is 0.25. I multiply those two together, and I get 0.5. Half of my observations are in the bin from 4 to 6. On the other hand, if I say what proportion of my observations are in the bin from 6 to 12, I take the width, which is 6. I take the height, which is roughly 0.042, and I multiply them together, and I get 0.25. So the area of those bins, the area of those boxes, those bars, is the proportion. The y-axis is density, and I have a question, or you have a question.
So what if you want to get the portion of the area between 2 and 5?
Good question. The question is, well, what if I'm trying to get the proportion of the population between 2 and 5? I would have to say I can give you a rough estimate of what that is. And does anyone want to come up with an idea? How would I estimate the proportion between 2 and 5? In the back, I saw you first.
So cut the first rectangle in half, find the area from 2 to 4, and then cut the rectangle from 4 to 6 in half, and find that area.
Right, so fortunately you chose some good numbers. So 2 to 5, the 2 is smack in the middle of the first bar. So I take the area of the first bar and I cut it in half, and I get 0.125. Then I take the area of the second bar, or I take the second bar, and 5 is smack in the middle of it, so I cut that in half. And that is 0.25 is half of its area, and I add those together, and I get 0.375. Okay? And that's what you do when you say this is rough, because in fact, you can, if you had the data itself, you would look at the data and you could say exactly what proportion of your observations are in that interval. With one of these smoothed distribution or density plots or histograms they've got edges, sharp edges, but in a way they're smoothing as well, that we can answer these questions only roughly or approximately because of this smoothing. So the same thing's going on with that very fancy thing I was doing with that kernel, and I was trying to say, well, I'm getting a little bit from this observation, a little bit from that, and I'm stacking it up, and that's how I get the height of the density. Same thing's going on here, but it's cruder. It's saying, I'm going to come up with an estimate for my density that's going to be the same from 0 to 4. I've got one observation in that, so I'm going to spread it all across that interval from 0 to 4. I'm going to come up with an estimate in the bin from 4 to 6. I'm going to make it all the same. Well, I got 2 observations in there. I'm going to take those 2 observations. I'm going to spread it all the way across. And that's how I get a flat top. So the difference with kernels is that you're not doing this sort of straight spread. You're, in fact, instead taking little bits from each of the observations as you move this small function along, small smooth function along. Yes, question?
So if we make all these bins the same size, and we'll call this size the width delta
Yeah, make
X.
it 1.
Right.
Let's make it all 1. Yes.
And then if we make the limit of delta X approaches 0,
Oh.
so we get smaller and smaller bins, eventually we'll approach the distribution we had for the normal.
So the question was, if we start shrinking the bin size, is what's going to happen when we shrink the bin size? You can, if you shrink it too much, you wind up, for a histogram, you wind up getting flat things and then big spikes right at every observation. However, it's the same idea as when we shrink the kernel. So I really like that question. If I start and I say, I'm just going to have one bin for my data, and it's going to go from 0 to 12. So it's just going to be one big box. And its height is going to be what? What's the height of that bar going to be? No, remember, 1's the area. Caught you. 1's the area. The width is 12. Its height is 1/12. So the height's 1/12. The width is 12. When you multiply them together, you get 1. Okay, so you get a flat bar. Then as I shrink, if I immediately go to bins of width 1, 0 to 1, 1 to 2, 2 to 3, you can tell me right away the height of the bin from 0 to 1. It is 0. There's no observations in that bin. And 2 to 3, well, then we get into this, am I counting it in the bin from 2 to 3 or the bin from 3 to 4? You just decide. That's called the endpoint convention. You decide whether you're going to always include them to the left or always include them to the right. Let's say we're going to always include them to the right. So from 2 to 3 is 0. From 3 to 4, I've got a bin. What height is it? What height's the bin from 3 to 4? You were about to say it, but you're not going to now.
0.625.
No, it's only a bin of width 1 now. Okay, the bin's width 1. It's got 1/4 of my data in it. So its height's going to be 1/4. So it's a height 1/4 times 1 gives me 0.25. So that's the magic, right? The area equals the percentage of the population in that interval. Good questions. Any others? No? All right. So why do we bother making these when we could just have all of our data? If you remember, I showed you all the data for birth weights on Monday, and it was just this huge mass, which I shrunk so it was really tiny so that I could fit it all on one screen. And you can't really see anything in there. You can't see anything about the real structure of birth weights. You might be able to sort of have your eyes scan over one line after another and kind of try to pick out or get a general impression of what are common values or what's a really small value or a big value. But a density plot and histograms are a real quick way for you to see the underlying main features of the distribution or the structure of the distribution. So we're going to go through quickly what those pieces are. There's the mode. The mode is any kind of peak in the distribution. Now you know whether you make a histogram or a density plot, that can be affected by how wide your bandwidth is for your kernel or your bins. So you want to be able to sort of not just pick out lots of modes where all the observations are, but you want to sort of have what you think are sort of true modes for the underlying distribution. Next thing is symmetry. That's whether or not there's a point at which if we drew a line, vertical line on our plot, we could fold the density plot or the histogram and it would look the same on both sides. There are many more distributions than the bell curve that are symmetric, such as the absolutely flat bin from 0 to 12 is symmetric. If it's not symmetric, we say it's skewed. And we usually like to say where there's more mass on the left or the right. That gets us into tails. It's nice to know whether our tails are long or short. Long tails means it falls off gradually. Short tails means it drops really quickly. So we saw with the birth weight data that it had somewhat of a long left tail. Oftentimes, long versus short, I haven't told you what that really means. Many people often use the bell curve as a baseline for comparison, and so they talk about long or short in comparison to the bell curve. Then there are gaps and outliers. There might be regions where we see no data. And so that's good information to know, is we saw no observations in this span. We want that to be what we think of as a relatively large span as opposed to something related to the fact that for example, birth weight was measured to the nearest ounce. So you're going to have lots of gaps that are at like 0.5 ounces, 66.5, 99.5, 100.5, 101.5. Those are not meaningful gaps. You want something where there's you wouldn't expect to see observations in the future. Question?
If we have a data set with a lot of gaps, we would increase the size of the bandwidth of the kernel.
Very good. That's right. So if you have data that's measured to the nearest ounce, then you want to have a bandwidth that's going to be able to pick up the observations that are 1 or 2 ounces away to contribute to the density plot, because you know that things that you were not able to measure things between 100 and 101 ounces. And outliers are unusually large or unusually small observations. And typically, we want to investigate as to how we might have that particular, how an outlier might have come about, or what that might mean in terms of the data collection process, if there was a mistake, or if there's real meaning for why we might sometimes have really large observations. Okay, so real quick, let's summarize in terms of modes, symmetry, tails, gaps, and outliers, the birth weight distribution. Okay, modes, what do you say? Is it unimodal, bimodal, trimodal, 1, 2, 3? Yes, it is one of those. Which? Unimodal. Is it symmetric? Say roughly symmetric. It's got this issue of the next thing, tails, with a slightly long left tail. Are there outliers? I would say there's some unusually small and a few unusually large babies, but not necessarily calling them outliers. So this is how I would summarize it. It's unimodal. It's helpful to say where that mode is. It's unimodal with a mode around 120 ounces. It's roughly symmetric. However, the left tail is somewhat longer than what we would expect, and some babies are as small as 60 ounces. There are also a few very large babies, larger than 170 ounces. So that's the kind of thing I'm looking from you for your first homework, is a way to summarize the distribution in terms of these concepts. Yes?
Then wouldn't the symmetry or the tails and gaps be kind of varying on your bandwidth?
Yes, the question is, am I going to get a different answer if I choose a different bandwidth? If I choose a really tiny bandwidth, I'll get a different answer. A really big bandwidth, if you choose a really big bandwidth, you get something that just looks nice and smooth like the kernel, basically. It's going to look like the kernel. And so that's the art, is that you want to pick a bandwidth such that you see the structure in the data and not the individual observations and not the kernel. So if you get too big, all you see is the kernel. If you get too small, all you see is the individual observations. So you play around with it. You change them until you see, you don't necessarily just go with the one that R gets you. You might change it, make it smaller and bigger, and see what comes out. Now it's your turn. 5 minutes you get to do this with 4 things, and I'm not telling you, don't have the data. So I want you, this is a thought exercise, now that you know all of these things. I want you to sketch what you think these distributions might look like. And we're going to keep it really short. The chest size of Scottish soldiers in 1817. Why 1817? Because that's when Quetelet measured them. The time the Cal students spent playing video games last week, well, actually, this is 10 years ago last week, data collected in Stat2 of all places. The annual money income, and that's the term used by the US government, money income, I didn't make that one up, of people aged 25 to 34. The number of children of women in the United States who are aged, not 40 to 4, but 40 to 44. So I'm going to split the class into 3 parts. Everybody does the chest size really quickly. Then everybody on the left, or my left, you folks over there are doing the video game one. The first half of this side, I want you to look at the money income, and the back people, the number of children. And get started, and then we'll talk about them. You have the time spent playing video games. And when you've done yours, talk to your neighbor, and when you've done it, go on to look at the others.
So we can make a sequence of things with days of the week on the x-axis and with the width of one. And I think what we'll find is that the majority of video games are being played on Saturdays.
So they don't have the actual days that they spent, they just report the time spent for the whole week.
I think we're just well, it would be, I think, because there would be a lot of people who is like new video games, right? And there would be a bunch of people who, so number of hours. We would get. I think that we would get a symmetrical curve. I think that we would find that it would look maybe something like
Chest size should just be normal.
yeah, a chest size would be a completely standard.
Okay, you guys ready? Shall we regroup? Let's start with the one that none of you have done. The Scottish soldiers. I have a couple questions for you about that. Well, first you tell me before I make any kind of comments. What do you think the distribution would look like? So what would the density plot look like for the Scottish soldiers? Yes, in the back.
Pretty much very symmetric bell curve.
So So therefore, bell curve means tails that are.
Yeah, pretty much no tails because there's not going to be anyone that's going to be extremely, out of their boundaries. I think that would be established.
Okay, so let me. So the comment was it should look roughly like a bell curve. Tails are not too long, symmetric, one mode. What information about Scottish soldiers did you use to come up with that comment? So we would sketch this roughly like that. If I had to put a scale on the x-axis, where's that mode? What do you think? Let's measure it in inches. Where's the mode?
34, 36 inches maybe.
Okay, I'll take your 36. So why did you come up with a bell curve? This is for anybody, not just for the person who answered the question. Why? Because why? Why did you come up with a normal distribution? Why does that make sense to you? Yes? Right, we talked about that on Friday. Things in nature that grow naturally often follow the bell curve in its shape. Why did you come up with 36? Eugene, you said 36. Why?
Because generally most people, their waist size
Mhm.
is about the size of their chest, especially like back in those days.
So back in
So,
what days? Yeah, this is
Like
200 years
17,
ago.
17, like this
right?
is- you know what I'm saying? Like people have like obviously like evolved since then, and we've all gotten bigger, stronger. You know what I'm saying?
So you're saying you think 200 years ago that the men might be somewhat smaller than they are today, so you pick 36 knowing what you think is an average chest size for today.
Yeah.
That sounds like a good reason. All right, let's move on to the next one. The next one is time spent playing video games last week. That's you guys. What do you think that distribution looks like? Let's get someone else. What do you think that distribution looks like? Yes? A peak closer, and what's the left side? In this case, what kind of lower bound are you going to put on it? 0. Some of you are saying 0 because why? Because you know you can't play a negative amount of time. So 0 is a natural lower bound. And what do you think about 0? Was it you that had your hand up just now?
Yeah.
Yes?
I think the peak's going to be at 0.
You think there's going to be a peak at 0. Why?
That's going to be the mode.
And that's going to be the mode. And why?
Because, yeah, I'd say about, like, I think 50% of Cal students haven't played any video games last week.
So you think there are a lot of people at Cal or students at Cal that don't play video games, hardly at all, and therefore not last week.
Yeah.
So what is this connected with in terms of one of the questions we looked at last week? The soda consumption, that's right. And so are you convinced? Well, what's your name?
Me?
Yes? Hannah. And your name?
David?
David. Did David convince Hannah or did Hannah convince David? Okay, David convinced Hannah that maybe there'd be a peak at 0. And then what's the rest of the distribution going to look like? Someone else aside from David. You had your hand up at the beginning. What are you going to say?
Well, I speculated that it might be bimodal because there's a lot of people who aren't going to play any video games. And then there's going to be some people, it's not like you're going to play 20 minutes of video games.
You got to
You're gonna
play it for a certain amount of time.
4 hours.
Okay, so you're thinking it might be bimodal for those who don't play it at all, and then further out for the people who play it some of the time. And you want to add to that?
Yeah, I think it might go slightly down between like 1 and 2 hours,
Uh-huh.
you said, and then
Right.
drop down and then like a higher peak at like a intense number of hours.
Like something like that is what you
Yeah.
are all saying. So it's got to have a short left tail because 0 is the smallest it could be, right? And then after that it's probably going to drop off. You think it's going to drop off dramatically, and then there might be another peak later on for the people who regularly play. Yes?
I think the left tail is going to go on really, really long. Or the right tail.
The right tail you think might be really long.
Yeah.
Why?
I think there's going to be some guys who play like 300 hours.
Yeah, right. So way out there might be those guys who spend a lot of their life playing video games. Okay, next one is the income. There we go. Money income of people aged 25 to 34. That's you guys in the front over here. What do you think that distribution is going to look like? You think it's going to be bell-shaped? And you are? Gregory? So you think it's, well, bell-shaped and long tail on the right are not quite the same. I'll go with a long tail on the right. But you think there's a big mode. There's a big mode more on the left and with a long tail on the right. And we know it's got to be stopped at 0. How about anyone else? Do you think that's a rough? And what do you think the range is here? This is from the current population survey taken just in 2008 or 9, so it's in today's dollars roughly. So I think what Gregory's saying is this. Is that right? Okay. Can you give me some locations of where you think that big mode is?
30,000.
You think it's 30,000? And you were going to say something different?
I think at least 40,000.
Okay. Roughly this. Let's go with roughly the same. All right. Last one. This is the number of children, women aged 40 to 44. You in the back, my first question to you is, how is it different from the other 3 things that we've looked at so far? There's something very different about these data. Think data type. You in the front want to answer it? Yes? You can't have 0.75 babies. Is that what you were going to say? That's right. So is this information quantitative? You were shaking your head, I think. Yes, it is quantitative, but it's very special. It's discrete in the sense of you can only have a certain values for it. So that says what did you draw in the back? What did you guys draw? That was your question? Any of you? You drew a bell curve, but wait a minute. A bell curve is for something that's continuous. You can have values between 2 and 3. You did like chunks? That's not a bell curve then. Mm-mm. I think one thing I'm going to hopefully get you guys to break away from saying everything looks like the bell curve. Because only one of these four might look like the bell curve. All right. Is somebody going to venture in the back what you think this might look like? Do I need to come back there? What do you think it's going to look like? Just take a guess. Yes? Several peaks at integers. Is that what you said? At integers. Yes, and in fact, because we only are allowed to have integer number of babies, we don't make histograms or density plots with these. We do something really different. So what's my first value? Good. I don't start at 1, do I? How far do I go? I could go way far out. I'm going to stop and lump everybody 5 or more together at 5. And what we do is we draw little spikes right on top of the integers. And this is the case where the height is the proportion, because there's no area here. You either have 0 babies, you don't have 0.5 to 2.5, it doesn't work that way. So the spikes actually equal the proportion. And tell me, what's the tallest one? 0? 1? 2? Okay, let's have a vote. Who says 0 is the highest? Oh, come on. Somebody said it. 3 people, okay. Who thinks 1's the highest? 2? Okay, so we'll make 2 the... Entire U.S. I've collected the data already, or not me. This is census data. Many of you think 2's the highest, so I'll do that, and I'll just make these smaller, gradually smaller. And what about 0? Somebody? Second what? Second tallest. Why? Yeah, why?
I guess I think there are a lot of women between those ages that don't have children.
There are a lot of women in that age that don't have children. And why did I pick that age, by the way, 40 to 44? Yes?
You're past the childbearing age, so...
Exactly right. You're past the childbearing age, and so roughly this is it. This is now looking at a sort of stable population in terms of number of children. I had no idea that only about 6,000 to 7,000 women over the age of 44 had children in, I don't know what, out of however many hundreds of thousands or millions of babies that are born in a year. So yeah, this is past the childbearing age. All right, now what I want to do is say, good job, very good job, and what we're going to do now is take a look at the actual data. So really quickly, there's Scottish soldiers. Yes, indeed, it is roughly unimodal with not long tails. And this time it's actually centered not at 36, but about 40. I think these are soldiers, so they might be more fit and bigger chest. Income, this is slightly bizarre looking. And there is a mode at 50, and there's kind of another mode at 25. And there is slightly long tail, but why not the kind of long tail we thought there would be? I have a guess as to why. Well, for one thing, these data are slightly fabricated. I just have them in intervals, and I smoothed it out. So there could be some way out there. The other is?
Well, it's 2008. Isn't that also like...
Well, that shouldn't matter. The year shouldn't matter that much. But what does matter is that these are 25 to 34-year-olds. So maybe the range of your incomes is not quite so large as you might think. Number of children are these spikes. And indeed, 2 is the highest spike at roughly 32%. But there are roughly 22% of women that have no children in this age bracket. Okay? All right, here's an alternative to making that chart for the women. You could make a bar chart, but remember the width of those bars have no meaning whatsoever. It's the height that matters. And I will see you all. Oh, wait. Time spent playing video games. Big peak at 0. And then, yes, indeed, there are a couple other peaks and a very long right tail for the person who spent 30 hours. See you all Friday.